A 2,000 kilogram car heading 30 degrees north of ease at 22 meters per second runs a red light and hits a 1,000 kilogram car heading north at 20 meters per second. Following the collision, the cars stick together and follow the same path. Determine the velocity of the cars after the collision. So as for inventory, we are given the masses of car A and car B and their initial velocities. So the physics principles we used was that the system consists of two cars, car A and car B, and that there are no net external forces. Therefore, the momentum is conserved. And so the change of momentum is zero. And so it's the Newton's second law in terms of a momentum. And we use the definition of momentum.
Okay, so here's our visualization for the two cars A and B. So at first, car A is going to be moving at a speed of 22 meters per second at 30 degrees north of east, okay? So then mass B, which is going to be car B, is going to be going 20 meters per second north. So that's going to be the part here, okay? So when we see these two things collide at the end of the collision, they're actually going to stick together, which is indicated here. They're going to be sticking together and they're going to go off together in the same direction and the same acceleration, okay? That was a visualization. Okay, so for the two masses, the two cars, what we first need to think about is the momentum of the entire system, and that's going to be displayed through this equation, okay? So when we look at this, we first have to find out if F net is going to be zero. So in our initial principles, we find that net external forces are zero. So that means that we can set change in P, which is going to be our momentum, to zero, which means that from this point, we can find out that the initial momentum was going to be equal to the final momentum. Okay, so first what we need to do is we need to calculate the x and y components of the velocity of car A. So if you see here, you can see that I split it into the two x and y components, and here I show the calculations for them. And the v initial x comes out to be 19.1 millimeters per second. So now what we go to is this momentum equation. So what it shows here is that the mass of the car A and the v initial of car A in the x direction, and the mass of the car B and the v initial of car B in the x component. And then at the end, because the masses combine, we actually add the two masses together. And then we have a variable here for the end velocity of the in the x component of the entire two cars. So if we go to the next part, we cross out this because the actual x component of the car B is actually zero. So we can actually cross that out. So it comes out to the next equation here. Okay? So now I just fill in the different variables for the stuff. And then we come out that the final x component of the cars is 12.7 meters per second here. Okay, so now we need to calculate for the final velocity of the car after they're combined for the y direction. So first what we need is the initial y velocities for the two cars. So then those are 11 meters per second and 20 meters per second. So then what we do is then we plug that into this momentum equation, which shows all the initial momentums and all the final momentums, okay? And in the second part, just like in the x momentums, we find that the masses are combined, which is why they're added here, okay? Now when we plug them in, we get our v final after isolating it to be 14 meters per second. Now that we have both of the v finals for the x direction and the y direction, we can use those in a triangle here to find out actually the angle that it increases at. So the final angle would be the inverse tan of 14 over 12.7, and then that comes out to be 47.8 degrees north of east. Now to get the v final, we use the Pythagorean theorem, and when we plug in the values, we get 18.9 meters per second for the magnitude of the velocity, and that'll be at 47.8 degrees north.
There are two misconceptions for this problem. The first is that you cannot just use the initial velocities as they're given. You have to break the initial velocities of both cars into their x and y components. The second misconception is that it may be thought that the velocities of the two cars after the collision are different from each other, but because they stick together, they have the same velocity.